we have these gas sensors and PM particulate matter sensors, ozone and NOx, or what we use for gas sensors, and particulate matter sensors. And these are commodity sensors off the shelf. You can buy them. These are all sort of manufactured in Taiwan and shipped over. And many of these sensors are used worldwide for many of these low-cost IoT devices, right? So there's nothing fancy we are doing on the sensing side of things, right? But again, these are connected through wireless mesh network using 6LoWPAN as the technology for the mesh network, which is an IETF protocol for low power personal area networks. And some of these devices also have 2G or 3G connectivity, right? So it's to sort of compare and contrast both a ad hoc network as well as a more managed cellular network, right? So these devices could have either of these technologies. And if in the case of a wireless mesh network, there would be a gateway device, which is a Raspberry Pi device that has some onboard sort of software running and some analytics running that would sort of interface with the cloud, where the actual data itself is curated, stored, and visualized, and so on, right? So that's sort of this idea. And down the line, you could also have sort of energy generation capabilities on the edge, such as solar panels or concentrators and so on. And this is actually a deployment that has been going on at the IIT Kanpur campus for the last year and a half. In fact, Shreya, who will be talking as part of the tutorial, she's sort of been leading some of this activity from the field deployment perspective. Again, as you can see, this has all the ingredients of an IoT network. You got sensing, you got communication, you got data analysis, and so on. There is no direct actuation in that sense from a closed loop cycle. From the domain perspective, there is no immediate feedback to the field because from a air quality pollution monitoring perspective, there's not much in terms of feedback you can do. There is obviously some simple things you can do, such as you can send alerts to people, right? In case the pollution level is going to go greater than some threshold. Maybe those who are suffering from breathing difficulties or asthma and so on, they might wish to get some notification. But other than that, there's no active control of an environment as such over here, right? So eventually, this data might be helpful for policymakers, let's say, to decide on various types of pollution mitigation strategies. It might help you locate where the sources of pollution are. It might help you identify what the pollution trends in different localities are across time, right? And it might even help, for example, if you want to plan a route through a city going from point A to point B, just like you can plan for shortest distance or least amount of time, you could very well plan for the least polluting pathway that you could take through a city as well, right? So this is much more from a data collection and analysis perspective rather than necessarily the feedback loop. But that being said, there is feedback loop at the infrastructure layer. For example, if we find that certain devices are not behaving properly, right? There, the feedback loop is to potentially look for alternatives to the device or potentially send someone to the field to fix that device, right? And we'll also see, we want to be looking at techniques where if you see certain sensors themselves degenerate over time, that might mean that you have to recalibrate the sensor and so on. So there is a bit of internal feedback that happens, but at the application layer, maybe there's not as much of a feedback loop. So a couple of interesting aspects to this particular project that we have examined. So one of them is to deal with the reliability of the system. How do you enhance the reliability of the system so that it can be more withstanding to failures? This could be failures in either the network layer or it could be failures in even the device layer, right? So over here, we have sort of done some fairly sort of straightforward work, I would say, in terms of how do you ensure that the data that's collected from the various devices themselves are sort of logged in like a transactional basis, and you sort of do some kind of a producer-consumer kind of model to collect data from the gateway from the various sensors, ensure that you log them into the local persistent store and then send it to the cloud, so that even if there's some intermittent failure of the internet connectivity, you're not going to be losing any data, right? So that's something that we've looked at. Also looked at sort of how do you potentially change the sampling interval, right? So at which the data is collected from the sensor. This might be important from either a domain perspective, where for certain periods you might want to run an experiment to collect more fine-grained data, even though it might cause a higher battery usage. But at the other times you might sort of collect data at a fixed sampling interval, right? So that's another kind of feedback loop you could have, right? So you can essentially have again, at the system level, you could have a feedback loop to change sampling intervals based on current energy consumption and so on as well, based on analysis that you do in a central location, right? But the more interesting part of the problem comes from how do you do better calibration on top of low-cost sensor, right? But before that, there's a few screenshot of this field deployment. We had some deployment happening at Delhi for a short period of time, followed by which the current deployment is at IIT Kanpur. And here is various visualization and so on of the field setup. And this is an example of the high cost sort of reference grade monitor that costs about $1 crore or so, and our corresponding low cost sensors, right, which cost about 10 to 15K or so. So let's get to one of the key challenges that we are sort of trying to solve as part of this problem. And this was also mentioned earlier on. One of the earliest questions we got today was, how do you deal with data quality, right, from these sensors, right? Because when you say something is a low cost sensor, effectively you're saying that the sensing technology that you're using, right, is something that's much more cheaper than the high grade monitors. And this sensing technology itself might have inherent inaccuracies that are introduced as part of this, right? So for example, for some of the gas sensors that we have, internally speaking, the sensor essentially has two electrodes within a certain chamber where that can sort of take in the ambient air, and then it sort of measures the conductance between these two electrodes that's within the chamber, and that itself is going to be a function of the density of a particular type of gas within that particular chamber, right? And this keeps sort of getting sampled periodically, and that is what is reported by the sensor as a, let's say, a parts per billion of a particular gas, right? So, but internally, what the sensor actually measures is actually a physical property, right? It's which in our case, it's actually called the outputs from the two electrodes O1 and O2. And internally, the sensor manufacturer has some kind of a function, right, which is called a calibration function that goes from the values of these electrodes, which might be expressed in millivolts or something like that. From that, you want to convert it into a density of a gas, right, or a density of a particle, which is expressed in terms of, let's say, parts per billion, right? So the manufacturer themselves has done some measurement in order to figure out what values of the physical measurement or the electrical measurement gets translated to what value of the gas density, right? This is called the calibration function, right? But another way to think about this calibration function is that you're given two feature vectors, O1 and O2, which are the measurements from these two electrodes. And now you want to fit a function that will predict what is the output in terms of the parts per billion, right? That's another way to look at it as a machine learning problem over here, right? And what we notice is for the sort of sensors that we were using, right, which are fairly popular sensors, it's called AlphaSense. It's used by many projects around the world. The manufacturer offers 4 different calibration models, which they say that these 4 will be suitable for different conditions, right? So you can sort of pick and choose from one of these 4, right? One thing that we did was to understand if any of these models, right, the 4 calibration model provided by the manufacturer, works well for us or not. And what we found was the answer was no, right? And one of the questions to ask yourself is, how should a calibration model be, right? One of the things is that a calibration model should be simple, because you don't want a very complicated one, because otherwise going from a numerical value to the final answer itself is difficult. It should also be explainable, right? Because at the end of the day, we're talking about science variables. So you don't want some magic black box that says that, okay, trust me, it goes from this input to the output, and it's reasonably accurate, but don't ask me how, right? So you don't want black box functions. You want sort of functions that can be explained through physics, right? And it has to be simple as well, and it has to be generalizable across time. It has to be generalizable across sensors, across seasons, ambient conditions, and so on. There's a bunch of, and this generalizability, as we'll see, is really the more challenging part as we go along, right? But how do these calibration models behave, right? for our own Indian conditions, right? And this is results from some experiments we ran at Delhi, right, about almost 2 years back. And what you see in yellow, and these were co-location experiments, because these are nice ways to understand how well your low-cost sensors behave by putting them next to a high-cost sensor, right? So that's what you saw the two pictures earlier on, right? These two are actually sitting. These two are actually sitting next to each other, right, in the same environment. They were both sort of measuring the same ambient conditions, right? And by comparing these two, you can figure out how accurate the low-cost sensor is relative to the high-cost sensor, right? At the same time, there's also a way to collect ground truth data, right? So effectively, you're collecting data from both these sensors, and you know that your high-cost sensor reading is sort of the ground truth. That's the predicted value that you want, which can also be used as a training data for the data collected from the sensor itself, right? What you see in yellow over here is the ground truth or the golden truth value given by the high cost sensor, right, the reference grade monitor. And what you see in orange is one of the 4 calibration models, A1 calibration model for the low cost sensor. And this is for the ozone data. And as you can see, the values are fairly far off, right? So they are almost like 2x or so higher in some cases. In some cases, they are actually 2x or so lower, right? They go in both extremes, right? But another way of like asking the same question is the accuracy good enough, right? Because sometimes an accuracy of even 70 or 60% or even might be good enough, and sometimes an accuracy of even 95% might not be good enough, right? So one sanity check is to sort of understand, for example, what is a healthy level of ozone? What is a safe level of ozone, right? And as per the US EPA, Environmental Protection Agency, so they essentially say that a level of ozone at 85 parts per billion is safe for a sustainable period. Anything above that is unsafe, right? Now the question is, how often do you get a value of the orange that is on one side of this dotted line, while the value of the yellow is on the other side? And as you see a lot of these false positives where the low cost sensor is saying that it's an unsafe level, though the reality is that it's at a safe level, right? So for the purposes of just health and safety, this might be one metric. But there may be other scientific reasons for this monitoring, where even this kind of a classification might not be good enough. You need a higher accuracy, right? But bottom line, this A1 calibration, as well as the 3 other calibrations, none of the 3. A1 was actually performing the best, the other 3 were even worse than this particular model, right? And so which you can see over here, A2, A3, A4 are also over here. And as you can see, A1 and A3 give the highest R-square correlation, while A2 and A4 are much worse than that. So the default calibration is not good. This is for NO3, and NO3 actually performs worse than NO2 performs worse than O3, right? So these are 2 gas sensors that we were calibrating, right? So one of the goals for us was to see if you can build a better calibration model, right? So but before that, some of the sanity checks that you have to do, right, is to sort of make sure that there are not, as in you have to make sure that the calibration model is really at fault, and there are no alternative reasons why you're getting a bad value. Because these were some things that we observed in the early part of our project when we had sort of initially designed our sensing box and sort of the embedded platform and so on. We noticed that there were soldering issues that was causing current leakages, right? All voltage was not stable and so on, right? And because of that, the data collection itself was faulty, right? So once you fix all of those things, right, you sort of at some point in time you realize that, well, the only explainable reason for why the outputs are poor is because the calibration model is inaccurate. So that's something to keep in mind when you're dealing with large complex systems that have a field deployment, right? So a lot of things can sort of potentially go wrong everywhere from your hardware to the communication layer to your analytics and so on. So you need to first of all figure out where the problem lies and fix one of them at a time, right? So now that we have realized that the calibration model is to blame, again, like I said, when you're doing such sort of task, it's always good to start off with a simple solution, right? So as they say, Occam's razor, sort of find the simplest solution that's good enough for your problem, right? So, and the simplest solution they can come up with for some kind of a machine learning model for prediction, right, is a linear regression model, right? So we sort of fit a linear regression model, and as you can see, the correlation jumped up from zero 0.4 for the default manufacturer model to 0.76 for the linear regression model. And you can see the trends between the predicted and the observed are much more closer together, right, compared to earlier on. Right? You still see some shifts over here, but they are not as dramatic, right, as the low cost, the default calibration models. And for O3, you see the a much better sort of correlation of 0.88, right? So at this point in time, you're really getting into a space where you're almost as good. I mean, think about it. You're paying 1,000 the cost and getting about 0.88 as a correlation. That's not too shabby at all, right? But then again, you can sort of do and then for PM 2.5, which is a particulate matter, you get even better, right? You're getting a 0.96 kind of correlation, which is almost as good. I mean, above 0.95, you're really, really doing good, right? So it's hard to find fault at that kind of a correlation, right? So this was good news for us, right? Which meant that we are able to outperform the baseline that comes from the manufacturer, right? So again, you also sort of want to try to see if you can do even better. And the next, maybe a bit more complicated model is a regression tree model, which we tried out, and we saw that the improvement was better in case of the regression tree model R3. It gives you a marginally better response compared to just the linear regression model, right? And here in R3, the additional features that we are using are the temperature. Okay, so one of the interesting bits, and here some of this gets into a domain-based tuning, and this comes from people who work in the domain, right? People who know the physics of how things work. And one of the interesting observations, at least for me, was that the measurement of ozone and NOx are actually related to each other, right? So they can actually influence each other, right? So even for predicting something like NO3, you actually feed in the features for the ozone as well as part of the input, right? And on top of that, you also feed in additional features such as the temperature that's measured from a temperature sensor, and also the humidity at that particular location, right? So using these 4 features, the 2 electrode values of the NO3, 2 electrode values of the NO2, O3, and the temperature and humidity, you can sort of build a regression tree model, and that sort of provides a better accuracy compared to the linear regression model. Right? Again, none of this is fancy at all. These are all just fairly run-of-the-mill techniques. But the point being that sometimes even a run-of-the-mill technique can give you a good enough jump from the baseline compared to more complicated models. So always start simple and then make it complicated based on need, right? So the solution should follow the problem, not the other way around. So that was sort of the good news. The bad news is that there are challenges in making this reliable across time and across cities. So, for example, we did deployments in Delhi, Kanpur, and Mumbai at IIT Bombay, and we find that it's the same calibration model is not good enough for all 3 locations. So you have to actually retrain the model for specific cities because Mumbai has a very high humidity because it's right in the seashore. Delhi is a very arid condition. Kanpur, IIT Kanpur campus has a very different locale as well. So you do have location-specific sort of retraining and calibration that's required. So that's something that we are looking into, whether it's sufficient for doing it at a city at a time, or is it sort of the microclimate within a particular deployment that's going to have an impact. Another question also is, what is the behavior across time, right? So this was done over a 3-month period where we did the validation. But across a year or 2 for a longer term deployment, right? How frequently do you need to calibrate? Is the monsoon season going to require a different type of calibration compared to your summer, right? Some of these sensors also degrade over time. So the calibration that you do in year 1 might not necessarily work for year 3, right? So there we are having to look at more complex models. Again, we are collaborating with other folks who work on machine learning to see if you can do things like transfer learning and so on in order to help sort of have more complex models, but that will be more robust across some of these variabilities. Right? So that's sort of the key summary of this particular project. The key outcome, again, low-cost sensors at large scale, looking at resiliency of the edge, and also calibration models to address some of the sensing errors, right? So some of the key takeaways from this project, right? So let me pause over here, see if there are any questions, and move on to the next two case studies.
Three questions. First one was regarding the challenges that we face. So you said it is always better to have fewer variables when you are making analytics and calibration. So how is fewer variables going to improve accuracy? Because the more the variables, the accuracy is better, right?
Right. So my point was, it's a trade-off between simplicity and accuracy, right? Uh, because one of the studies when we started sort of collaborating with a machine learning colleague, and they threw in pretty much all kinds of complex models, right? And the accuracy went, like, correlation went up from, let's say, 0.88 to 0.92, right? Now the question is that incremental improvement, right, good enough for a model that's much more black box compared to a linear regression or a regression tree model, right? And some of the scientists that we work with, right, and this is coming not from, this is not my opinion, but the opinion from the domain scientists, they essentially say that, hey, beyond a certain point, meaning we don't want black box models, right? We'd rather something like 0.88 is a good enough correlation for us, is a good enough accuracy metric for us, right? That any incremental value that you get from a complex model might not be worth it, right? Adding more features, for example, adding a temperature sensor and humidity, right? That actually did have a marginal impact, even with an regression tree-based model, right? So it maybe bumped up from the point from 0.7 to 0.8 or something like that, right? But there again, the question becomes that what are the errors that are going to be introduced by the low-cost temperature sensors and the low-cost humidity sensors? Will they themselves degrade over time, and they will start to sort of add to the error rather than correct for the error, right? So the end of the day, it's a trade-off, right, between accuracy and simplicity, right? And the sweet spot might be different for different applications.
So another question was, we said that it's always going to be a combination of the central control system that we have already in place, which is quite expensive, and the combination of these low-cost sensors that we are going to deploy across the place. So where do we draw the line? Which control goes to the central control equipment, and which actually is more heavy? I mean, useful when it comes to low-cost sensors. Where do we draw the line?
Right. No, those are great questions. Some of these get into, again, there it becomes a cost versus accuracy trade-off, right? So you might sort of have a certain budget, and the question is, for that particular budget, how many high-cost sensors do you want to buy, and how many low-cost sensors do you want to buy, right? That's one way to look at it. The other might be from an accuracy perspective, right? How do you want to even deploy these high-cost and low-cost sensors in different locations? Because you might be able to do some extrapolation. If you have a high-cost sensor deployed in a certain layout, right, and low-cost sensors spread all across them, you can do different kinds of interpolation and things like Gaussian mixture model and so on to actually correct for some of the errors of the low-cost model using the errors, I mean, the values you see for the high-cost model, right? All of these are open research problems. There is no single solution for that, and these are actually stuff that people are working on as we speak.
And the third question was on you. We discussed about, is the accuracy good enough? And, how every sensor might work differently in different locations.
Yeah.
So are our systems, or in near future, will become intelligent enough to categorize the reason for air pollution? For example, some places you might install, and you might know that the place has more of stubble burning, and in a city we know that it is more because of the emissions. And in industrial areas, it could be because of any toxic are burnt. So there are many factors. So are our systems, towards getting intelligent enough to identify and categorize, and mitigate the problem? Or is it still a long term goal?
Right. No, I think it's definitely a long-term goal, though we are not looking at it as part of this particular project. I do know that my collaborator Tripathi from IIT Kanpur, he does work on this, the causality, as one of the key research problems. And there they also use, for example, data from satellite imagery, right, to try and correlate some of these aspects. They also look at things like wind patterns and so on to understand what the flows might be and so on. So those are much more complex problems, right? Especially if you want to solve them using simple sensors, right? So you can always have sort of some kind of a hyperspectral imaging that will tell you exactly what the components of the air are, not just the ozone and NO2 and so on. And that might actually give you a signature to what the source was. But obviously, we can't do those at scale, right? So these are still open problems. There are very rough solutions out there. But one of the goals, meaning even as part of the national like the air pollution monitoring mission that was rolling out just before COVID hit, and it's sort of in a pause right now, is to have more data collection, right, in different cities at large
It
scales.
could be a combination of practical aspects. Let's say we